Okay. Because I think that maybe yesterday for some parts at least of the lecture that the mute was enabled, and then I don't know if you have a reasonable voice anymore. So I'm not sure. Whatsoever, I cannot change it. So, I think your best ask him later. Huh? Good. Let's immediately start. I think there's not too much to recap. We derived yesterday together this shift and add multiplier. So the only thing maybe to recap is what was the problem here with the sign bits? What do we have to do if we have a negative b value? So assume you have a negative value of b. What do we have to do? We need to change effectively the sign here, ensure that here is a positive sign bit. So we can either switch, or we can always, if this here is negative, build the 2's complement of these two. And then we have always here a positive number, and if this is positive or negative, it doesn't hurt. So, good. Then we extended this a little bit to the CSA, which is, I would say, more or less straightforward. So the only thing is that now we have the intermediate values here, which are carries and sums, some bits. If I do it like this, what is my longest critical path here? So effectively, somehow down here. So to this register. That's the longest path we can find. So what does the CSA then help? Because we could just use the adder. So there are two possibilities what you can do. The one is you run here with full speed. So with the speed of the CSA. And then for the adder to do the final, because we need this adder only once at the end. We do not care if there's some intermediate values that are just wrong. This is a carry safe adder. Yes. That's just this flip-flops, and this is a classical adder. Can be Cocker-Stone, can be Hunt-Carlson, can be Ripple carry. And this one here is actually slow. This one here is actually fast. Because this here is only one full adder. So here, today I have nothing with me somehow, but I think there are two things here. So the this one here is effectively this classical structure XOR. Then we have another XOR for this carry. This gives the sum, and then we have the end of these two and the end of these two, I think. Should it be? So if I remember correctly, which gives us the carry bit here, right? So two input bits are converted, or three input bits. So we connect one here, one here, one here. So these three input bits are converted into one sum bit and into one carry bit, right? All the time. And at the end, we need to sum up all this carry and sum bits, right? So that we have one binary representation again. Now, this one here is fast because the critical path here is XOR and OR. So 3 gates at most. This one here is slow because there are more gates involved, because we need the carry propagation from the very last to the very first. The carry propagation is here avoided. So in that sense, this here is fast, this here is slow. But this one here is definitely needed for the final, or something like this is needed for the final computation. Now, what can you do? You can run with the speed of that one. and then implement some wait cycles to ensure that this adder has sufficient time to compute the final result. One option. Another option is you just remove this and continue running the CSA. So if you continue running the CSA, then what happens is that for a while you have here zeros implemented, right? So virtually that means you sum up always then the carry and sum bits. So you implement actually a serial adder then for all the different positions, and you sum up until the result is settled. Then you can further run with the speed of the carry save adder. Make sense? Or was it maybe a little bit too confusing? So you go here. If we feed in, at this point we said, okay, we switch to the classical adder. But you could also say, I add at this point a 0. If I add here a 0, then what would happen? We have here, let me see that I can somehow resume it. This here is settled, right? Then we have here 1 plus 1 would be effectively 0 and 1 carry. Correct? No, 1 plus 0, sorry. So we would have to add up this 2, yeah? Plus an additional 0 because we only add 0. Yeah? So the result here would be a 1. We have here a 1 and another 1 that we have to end up, plus a 0. So we would have a 0 and a 1. Right? We have here, we have a 1 and a 1. Gives again a 0 and a 1. A 1 and a 0 gives, let me see, that was already where yesterday struggled a little bit because it, let me see, there's 1 is somehow missing. It was correct at the end, but I somehow always overlook it. So we have this one here. Yeah, this one here I think I skipped. That is why here we have actually, let me step one step back, just that I have at the end the correct result. Yeah, it's fine. We have here 1, right? 1 and a 0. Correct? This is just this line here more or less summed up with a 0. And it is a 0 at the input. And now this bit here is settled. Just as we had here, that bit, that bit, that bit, that bit is fine. We are now, this bit is fine. Yeah? Nothing to be added here. That's the same point. We add another time a 0. Yeah? So what we add are these 2 bits, and these 2 bits. So we have here a 0, no carry. We have here these 2 bits, a 1, no carry. We have here a 1, a 0, 1 carry. Right? That is what happens. So this bit here is already settled. Then we add effectively another times 0. Now this one here becomes a 1. Sorry. Yeah. A 1, no carry. These 2 here is a 0, no carry. This one here, effectively corresponding to that, is a 1, no carry. So we have now this one computed, and then effectively in the next step, this one computed, in the next step, this one computed. So if we just run further our KSF adder, the carry also propagates, just because we have the wiring accordingly. So what I try to say is, if you want to run without this adder, you can do it. You just need another few clock cycles until this carry here propagates out. Which means we will need, I think, once the length of A. So, yes? that was where we ended yesterday, approximately. Still, for this adder structure, we have a lot of computation steps, right? So the question is, can we do better? And the first thing, what we do is we use partial products. What means partial products? So let's go for a decimal representation, something like, don't know, let's say just that it's not binary, yeah, 12 times 12, should be 134. We have effectively 1 times 12 is 12, 2 times 12 is 24, right? Effectively, the outcome of this basic elementary things we can see as a partial product. For decimal, it works only half the way. Why? Because we have here this carryover. For binary, that's much better. For binary, if we have two numbers, let's say 101 and times 101, then our first step is, let's start with the LSB. MSB doesn't really matter, or with the MSB, well, 101. We add 101, we 000, we add 101, right? And then we add up. So a partial product is we multiply this here with this here. We multiply this here with this, we multiply this with this. Gives us these three partial products. Now, if you want to implement or compute here the partial products, what do you need to compute, logic-wise? So adders, you need to sum it up at the end. But if you only want to compute here all these individual values that are in this matrix, well, you can do most of the stuff with multiplexers, but what is the input of the multiplexers then? So let's say we have this number, yeah? Let's say we have 101 times 101. And we only consider the first line. What is the logic equation or the logic operation we need to come from I multiply this value with 1 to I want the output 101. What's the logic operation? So OR, AND, NOR, NAND, XOR. It's an AND, right? So effectively, we have an AND gate between this and this gate, gives that bit. So computation of these partial products is pretty simple. It's just AND gates. So with several AND gates, we can just do this, yes? So we just compute all this AND gates, and this one here is actually this here for the first step times this. This here is for the first step, also this one here. Yes. You know already that to compute in this matrix a specific bit, you need to take the index here of the row. So second row, this one here, times AND. Let's say we want to compute this one here, second index. Yes, that doesn't matter. I just, because, well, I'm used more to compute it like that. So that's why I start with the MSB, but we can also do this with the LSB. That doesn't make a difference. It's just we have a matrix, and in this matrix we can pre-compute all the partial products without actually starting with doing the sum, right? So that's what we usually do. We usually first write it up, and then we build the sum. Okay, that is what partial products mean. Now, well, we construct them in a matrix. So I just abstract from this concrete example I just had on the table to I have a specific position, and this position is implemented as or visualized as a dot. So if I want to compute, for instance, let's say this bit, I know this can be computed by, we have the second row, so we have this bit and the fourth bit here, this bit. Yeah? Same as before. Good. And now we can try to rearrange our operations. Similar to what we did for, let's say, the addition, that we tried to rearrange the operations of this addition. We now rearrange the additions here. And, well, then we can, of course, sum up with this matrix multiplier, yeah? Which is just what we had in the adder part, and we said that's not actually useful, but we can just input all our partial products to this matrix structure, and the outcome will be the multiplication result, right? Maybe not the most clever way to do this computation, but we can split our multiplication into other parts. Namely, we can always collect 3 or later 4 terms that corresponds to the same power of 2, add them up, and compress them with our carry safe adder. And then we can start to do this in parallel. So what we effectively have then is this Wallace tree construction, Wallace tree multiplier, where I yesterday said, or day before, that I will explain this with the multipliers. So we first want to do this with carry safe adders. I first want to explain what actually the indexes mean I have here in the slide. B0 till B7, I have just, we could also extend this to further bits. This is just the value, the bit value of the multiplier. Yeah? So A is the multiplicand. So the left side is A, the right side is B, and we do this bitwise because we want to compute this end. And the first line effectively is B0, so this bit ended with this one here. Now, then I have here the inputs to the carry safe adder. Upper indexes should be clear now. Lower indexes say this is a carry computed from inputs 5, 4, and 3. This is a sum bit computed from 5, 4, and 3. Just that we have a little bit in mind which columns here, which rows here we already collected. Okay. Now I take my matrix and I split my matrix into columns of 3 and into 3 rows always. So I take the first 3 rows, second 3 rows, and there are no more 3 rows, so I just skip this for the moment. I apply the input here, the 3 inputs, to my carry safe adder, maybe the green one because it's the LSBs. The other here to the orange one, and then the output will be some carries and some sum bits. So the first sum bit actually does not need a computation. That's why I marked it just in blue. So it's just not derived from here, so nothing new, but it's just taken from there. The same, this sum bit is just this input. I don't need actually an adder there. I can just put the input to the output. Because what I do is I apply here a full adder with C in, A and B, as we had this, and output here sum and carry. So if I input in this structure only 1 bit, the output will be this 1 bit. So this is why this here is just forwarded. When I have more than 1 bits, I have potentially a sum bit and a carry bit. So for all the other cases, I have from, let's say, from this block here, I have 1 sum bit and I have 1 carry bit. I put them to different positions because this here corresponds to 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, and so on. And that I just do for all these positions here. which values precisely comes out doesn't really matter. I only want to know what do I need structure-wise for carry safe adder. So this one here is the right one. This one here is effectively the left one. It's exactly the same. So this bit here goes directly out. This bit here goes directly out, and the rest is computed always with sum and carry bit. Okay. Now we are here. We have a new matrix that we can operate on. So what we do is, well, again, we take 2 times 3 and compress it. And that is what we see on the next slide. So we have this, the new matrix from the previous slide, and we take effectively 3 bits, 3 rows, top, 3 rows bottom. We apply again the carry safe adder. So again here we have a full adder where we have the 3 inputs and we have the 2 outputs. I don't know why, at some point changed here carry and sum for the upper lines, but it doesn't really matter. Okay, the same for the lower one. So we have 2 lines top, 2 lines bottom. Good. Structure-wise, we connect the carries to one adder, to one carry safe adder, and 2 new inputs. And we connect this sum, this carry, and this sum to the other adder. And then we have some sum bits that is computed from 5 to 0, some carry bits that is computed from 5 to 0, some sum bit that is computed from 7 to 3, and 1 carry that is computed from 7 to 3. Then we do another step. So again, we collect here 3 rows, apply a full adder. Only thing that changes is that I now, to have more space, change the direction where I draw this, and have the 2 outputs here. Right? Just the same as before. So in our circuit structure, we connect the sum here to a carry safe adder, and this carry and this sum to the same carry safe adder. Of course, we need to ensure that the same powers of 2 come to the same full adder and so on. But concept-wise, we just have a carry safe adder there and compress now to a carry that considers already parts of 7 till 0 and a sum that considers already 7 till 0. So we end up in this new structure here, again 3 lines. So we add another carry safe adder, which compresses now these 3 lines that are left to 2 lines. So we have from here to here, we have another carry safe adder, 3 inputs, carry and save and output. Okay? Carry and sum. Gives us here an output that actually collects all the input and compresses them into some representation of the result with 2 bits. And now we need to convert this 2-bit representation into a 1-bit representation, which means we need a classical adder for all the sums, all the carries, and then we are done. Right? Okay. Concept, okay, or? We can do the same with a compressor. So we first take the upper 4 and the lower 4. Gives us these 2 compressors, outputs, each carry and sum. We take another, we take then on these 4 outputs here, we make another compressor, puts the 4 inputs into 2 outputs. And then we take these 2 outputs to a regular adder, and we are done. So what do we win by such a structure? So compared to this matrix multiplier we had before, let's compare this here with the matrix multiplier, because this matrix multiplier was built on carry safe adders. Would you say the area is expected to be much smaller? The area should be not much smaller, right? Because the area, we need all the carry safes and we need all to collect this. What about the timing? Which one? This one here? Well, here the critical path is from up there through 1 carry safe adder, 2 carry safe adder, 3 carry safe adder, 4 carry safe adder, and then a classical adder. So 4 carry safe, 1 classical. If we go up to this matrix multiplier, this is only 4-bit. Yeah? So for 8, I would have here another, how many? So we have 3, 4, 5 inputs, 6, 7, 8, 3 more. Yeah? So we have effectively would have 6 carry safe adders plus a classical adder. So it has a long critical path. Yeah? We can generalize this a little bit. That's given here. So I start probably from the bottom. Yeah? And I do this, how this is computed only for this compressor, because since the compressor has 4 inputs, 2 outputs, we can operate with powers of 2, and that makes it easier to understand. Yeah? So we have here latency 1 clock cycle because we have no register in between. Of course, we can add some to speed it up. Yeah? We can do intermediate registration and can all do pipelining, all the stuff, whatever we want. But for the moment, as it's drawn, it's 1 clock cycle. We need first to generate all the partial products. Yeah? That adds to the area and adds also to the delay. But then, what do we need for this from the compressor wise? We have effectively in each, if we start from here, we have 1. Then we have here 2 inputs, 4 inputs. The next level would have 8 inputs. So we effectively double in each level the number of inputs we process. Huh? Meaning that's exponential to the top. Meaning if we ask how many levels of compressors do we need, then it's logarithmic. Huh? And since we compress down not to 1 but to 2, we have log 2 of n half. Huh? So we have effectively the first one has, let's say, 32 inputs. Then the next has 16. The next has 8, 4, 2, 1. The one we don't consider, so we have 5. The first effectively was inputs, not compressors. So we just need to count effectively the outputs. Then we need the layers of compressors. So we have 4. For 32, we only need 4 layers of compressors to finally compute the output. For 64, we only need 5. Which is very good because this logarithmic behavior means, well, even if you increase the length of your multiplier, of your input data worth, is not a linear behavior like for this matrix multiplication. Good. So we have log 2 and half compressors, approx because it exactly log 2 and half if we have power of 2 as inputs. Then we have an area which is n times n AND gates, an adder, and then we can count how many layers we have for this. No, we can count for each layer how many compressors we have. And we have, obviously, for this level we have 1, for this level we have 2, for the next level we would have 4, then we have 8, and so on. So this actually exponentially increases. So if 1, 2, 4, up to 2 to the power of log 2 of n half, which is just the depth. Yeah, minus 1 because we start with 1. And if you just put this series into, or look up what the series actually is, then it comes out it's n half minus 1. Yeah? So we are linear in the number of input bits, what we need as hardware, and we are exponential, logarithmic in the runtime increase if we increase by 1 bit, yeah? Which is pretty good. Yeah? So this is something which is also used in CPUs. Okay. Questions to that? Then we can do something which is computation different radix. So let me just see. Yeah, yeah, we can go directly for that. That is usually, let's say, a little bit tricky to get it, but it's not super complex, I promise. Okay? So we start maybe here with an example I give. Let's say we take a number, I make it like this. Yep. Then, if we compute this here in a classical binary setting, we add up 0, 2, 0, 0, then we add up here 2 to the power of 0, 1, 2, 3, 4, 2 to the power of 5. I think that's a little, I need to write larger that you can read it, right? So that was the number I had. And we have here 2 to the power of 0 times 0. This here 2 to the power of 1. This corresponds to 2 to the power of 2, 2 to the power of 3, 2 to the power of 4, 2 to the power of 5, 2 to the power of 6. I think before I had 0 more, but it doesn't matter. Yeah? So then we multiply effectively these values if we transfer into that decimal, and we have 2 to the power of 1 plus 2 to the power of 3 plus 2 to the power of 4 plus 2 to the power of 5. So let me, we take it like this, 2 to the power of, no, that's 0, which is 2 plus 8 is 10, plus 16 is 26, plus 32 is 58, if I count correctly, right? Is this correct? Yeah? Okay? If it's wrong, then we will at the end wonder why the result doesn't work. Yeah? So, now I can do the following. I can say 2 to the power of 5 is the same as 2 to the power of 6 minus, no, other way. I can say 2 to the power of 5 plus 2 to the power of 4 plus 2 to the power of 3. Oh, I start from the bottom. I can say 2 to the power of 1 is the same as 2 to the power of 2 minus 2 to the power of 1, right? Because this is always the half of that. Instead of writing this here, I can always write this difference. So, I can continue this here. 2 to the power of 3 is effectively 2 to the power of 4 minus 2 to the power of 3. Yeah? I remember this 2 to the power of 3. 2 to the power of 4 we just keep in mind. 2 to the power of 4 is 2 to the power of 5 minus 2 to the power of 4. So we have 2 to the power of 4 here, it cancels out, so we have 2 to the power of 5 minus 2 to the power of 3. 2 to the power of 5 is 2 to the power of 6 minus 2 to the power of 5. So this is, we have here, can write 2 to the power of 6 minus 2 to the power of 3 plus 2 to the power of 2 minus 2 to the power of 1. This is, what is it, 64, right? Minus the 8 gives 56, right? Plus 4 gives 60, minus 2 gives 58. It's the same, okay? So, just a mathematical trick. Now what did we do? Effectively, we interpreted this one here as this corresponds to 2 power of 1. This here corresponds to 2 power of 2. This here corresponds to 2 power of 3. This here, just write maybe here, corresponds to 2 power of 4. This here 2 power of 5. This here to 2 power of 6. Yeah? And 1, 0 represents minus 1. 0, 1 represents a plus 1. 0, 0 represents a 0. 1, 1 represents a 0. So, this here would become minus 1. This here would become plus 1 times 2 to the power of 2. This here becomes minus 1 times 2 to the power of 3. This here becomes 0 times 2 to the power of 4. This here becomes 0 times 2 to the power of 5. This here becomes plus 1 times 2 to the power of 6. Right? So we interpret now this number in a different way. And this reinterpretation here, also called redundant interpretation, because 0, 0 and 1, 1 are both interpreted as 0, leads to the same result. Okay, so that is what generalized stands here. If you have a long sequence of powers of 2 in your sum, that corresponds to a long sequence of 1s in your binary representation, then you can write it as 2 to the power of n plus 1 minus 2 to the power of m. Nothing else is written here. That's this example. Okay, that means instead of, I just keep this for a moment because I need to ask one additional question that we can easily clarify here. That means instead of doing a multiplication of a long sequence of a number with a long sequence of 1s, which are a lot of single lines we need to add up, we could do an addition of this number with only 2 bits. And instead of addition, we need a subtraction. That's it. So instead of multiplying here with this one here, adding up 0 times this, plus 1 times this, plus 0 times this, plus 1 times this, plus 1 times this, plus 1 times this, plus 0 times this, we can just pick the 1s effectively and, let's say, subtract this, add this, subtract this, nothing, nothing, add this. So we can reduce the number of actual adds we need, right? Not in the worst case, but on average. Why not in the worst case? So if all are 1s, let's skip this for a second. Let's keep the last bit a 0, yeah? Because otherwise we need to rethink what we do. So if all bits are 1s, the MSB and the LSB we keep at 0 for reasons. What happens then? Yeah, so we only need 2 operations. Actually, that's the, let's say, optimal case. Yeah? What is the worst case? Well, if you would have a sequence like this, then you would have the, let's put a 0 here, you would have subtract, add, subtract, add, subtract, add, subtract, add. Yeah? Means in the worst case, we need at the end then as many operations as we need for classical shift and add. Yeah? So on average, this is faster, but it's not constant time. In the worst case, it's as slow as a classical shift and add. In the best case, it can be faster. Yeah. Good. Then he pushed another interesting case, namely a sequence of all 1s. Yeah. That's actually why I kept this here. So let's say we want to now have here, instead of the 0, I put now a 1. So that means we have here 2 to the power of 0, and this number here is 59. What to do to keep this here correct? In a sec, I just first want to finish this one here. So if we here want to keep this correct, the correct 59, we need effectively, we can add 1, yeah? But then we have some let's say, ugly behavior, right? We can also say we remove this here one, this one, because then this here is again a 0, right? So this here becomes a 0. And we have here 2 power of 0 subtracted, right? So 2 power of 2 instead of minus 2, we have now minus 1. So this should increment by 1. So this becomes 59. Right? So somehow we now realized here a minus 1. Right? If we want to realize here minus 1, this here should be an artificial 0, which we can interpret, for instance, in a binary domain as 1/2. It's just a fixed point computation. So this is, now we have added this. Now let's go back to the case of 58. What happens for the case of 58 if we have here a 0 again? Well, then we have here 0, 0. That would result here in 0 times 2 to the power of 0, according to this rule. So 0, 0 is a 0. So the result would still be correct. So we can always just add here an artificial 0 at the end, and we do not change for the case that this bit was a 0, and in case that bit was a 1, we have the correct result with this interpretation. Right? So the rule is 0, 0 is a 0, and 0, 1 from the right to the left is a minus 1. So adding here a 0 for the case that we have a 1 at the end leads that this is a minus 1. If we have a 0 at the end, it leads to 0 times 2 to the power of 0, which is fine. Yeah? So that's the one side. What is the other side? We can have a 1 at the very beginning. Yeah? So maybe we make a shorter number just to show this. So we have something like this. Maybe I do this in black. Yeah? So we have 1, 0, 1, 1, and a 0. We do our interpretation here. This here gives minus 1, right? This one here gives a plus. This one here gives a 0. So here we have 0. This one here gives a plus 4, 2 to the power of 2, right? This here gives minus 8, right? Correct? Okay. So the result here is minus 8, minus 4, minus 5. Okay. Now I do the following. I take this here, invert plus 1, because maybe that's easier feasible. If I invert this here, I have 0, 1, 0, 0. So if I add 1, I have 0, 1, 0, 1, which is binary plus 1, right? Plus 5, sorry, right? So what did I do here? Effectively, by interpreting this in that way, this is automatically interpreted as 2's complement. So if I say I take just 2's complement numbers, what I do here is correct. I do not have to do anything. So that is already fine. We just need to keep in mind this number is a 2's complement number. The first bit is a sign bit. So effectively, here I should have written formally a minus 2 power of 6. Because it's 0 times 2 times minus 2 to the power of 6. Here we have plus 2 to the power of 6, of course. Okay? Okay, now you had a question regarding this sequence. So we interpreted here, we have computed these values. That was clear. We have computed from that which multiplication comes out, which was that. Then we have said we can transform these 2 bits, 2 to the power of, I just go back to the blue example. So maybe I make here a 0, here respectively a 0, and here 2 to the power of 2 of 1 minus. So that the blue one counts now again. Just to have, I stay with it doesn't matter. So I I just go for this one here. We have said we can interpret this here as, instead of 2 to the power 5 plus 2 to the power 4 plus 2 to the power 3, as 2 to the power 6 minus 2 to the power 3. Right? Now if we then look back what we actually did, is equivalent to, we interpret this sequence here, 1, 0, as a minus 1. This 0, 1, 1 as a 0. Yeah? 0 times something here. This here as a 0. This here as a plus 1. Because plus, so this here is minus 1 times 2 to the power 3. Is this one here. Right? So this one here is this one here. Because I have here this operation. Right? I want to minus here because I transform this 2 to the power 6, this long sequence of plus into the largest value plus 1 exponent minus the smallest value. Right? So that is, I say, effectively what I did here, I interpreted, because if I do this bitwise, yeah, this one here should be a plus. This one here, if here is 0, 1, we said it should be a plus. If you have a 1, 0 here, it should be a minus. Yeah? Okay? And then I just noted down these rules here that I identified here into this table. Yeah? So, in other words, we have developed an algorithm where we parse an arbitrary string if at the end we have a sequence from right to left, 0, 1. So if we see this switch in this direction from 0 to 1, then we should subtract. If we see the switch from 1 to 0, then we should add. And otherwise we do nothing. Right? We just can parse over the string. Make sense? Okay. Good. Then we have this done. I remove this here. And we have this, let's say, less concrete on the next slide. But in an, or more concrete, less, no concrete numbers, but more general, which is called a Booth algorithm and does exactly what we did. So we know we have a sequence of ones starting from the LSB, and we have a pattern 1, 0 in this, so the end of the sequence. Then we know we need to subtract. If we have this 0, 1 pattern, so we have the end of the sequence, then we need to add. That means we can write an algorithm, parse through our string. Before we can do something, we append the 0, this artificial 0 I had, just to be always correct, to have no special case for the last bit is 0 or the last case is 1. Last bit is 1. And then I always take a tuple of bits, mi minus 1, pass through my bit sequence, and if I see there's a 1, 0, then I subtract. If I see there's a 1, then I add. And then I need to multiply by 2 each time, because we want to take the next number, which is we shift. And the shift now we can do also if we have here 0, 0s or 1, 1s. For the MSP, we don't actually need to do this shift, we can do it. It doesn't really hurt. It's a matter if we have spent an additional register or not. Okay, good. Okay, I want to do one toy example. Unfortunately, I have no paper with me, so I need to do this on the table. But I will still take a photo afterwards and provide to you. So, we have this algorithm. I just put it, maybe do it like this. Then I have more space, and I do not need to write somewhere into the text. So we have this algorithm, and we want to do a multiplication. Tell me a number, don't know. Let's say, don't know, 5 times 8. Something which we can easily compute. Yeah, we do not need a calculator. So let's say we want to compute 5 times, or let's say minus 8. Hmm? So that is our decimal representation. So what we want to have in binary is 0, 1, 0, 1. Yeah? We need 2's complement numbers because we rely on that this is 2's complement. And we want to multiply with minus 8. So 8 is, let me think, maybe 8 is not the best number, but let me think a second. So 1, so no, 8 is no good number. I take maybe, don't know, 11, something like this. So we need something where we see some number. All right, I do it the other way around. I just write maybe this one here. Huh? So, which is minus 9, right? Correct? So if we invert, we would have 0, 1, 0, 0, 0, which is an 8. Add 1 is a 9. Huh? So this should be a minus 9. Yeah? Okay, now we want to do this computation with our Booth algorithm. So what we do is, effectively, we take the multiplicand times 1, 0, 1, 1, 1, and we append this artificial 0. Right? Now we take these 2 bits, or maybe do another thing beforehand. Namely, we call this here M, this here R, and doesn't matter. And we have on top, I think we do it the other way around. Give me a sec, just that I have the naming correct, with consistent with my formula, with my, yeah, that's fine. So this here should be R, this here should be M. So minus 5 is, we can pre-compute, should be this one, right? So inverting this gives 1, 0, 1, 0. Add 1 gives 1, 0, 1, 1. So we do this multiplication in that way. We see 0, 1, 0. So we have a register. In our register, we have, let's say, 4 zeros. And I have here some buffer. So we add to this register, I write here what I actually do. Effectively, we have to plus R. Sorry, minus R. Because this is minus. So, minus R, we have here 0, 1, 0, 1. Gives, effectively, what we computed is 1, 0, 1, 1, minus R. Is effectively minus 1 times 5. Yeah? So it's minus 5, right? This here is minus 5, and we just computed here minus 5. Because we multiplied minus 1 times this. Then we do a shift. So we need to do a sign extension. So this here is still minus 5, right? It's just now a 5-bit representation of minus 5. So if we invert, we have 0, 0, 1, 0, 0. If we add 1, then we have 0, 0, 1, 0, 1, which is 5. So it's still a minus 5. It's just a longer representation. Correct? Now, we are done with the first step. We take the next 2 bits. 0 means we only need to shift. Right? We do sign extension. 1, 1 is 1, 0, 1, 1. This is effectively what we computed is 0 times minus 5, or let's say plus 5, times 2 to the power of 1, minus 1 times 5 times 2 to the power of 0. That are the computations we did so far. So it's minus 5. It's now just a 6-bit representation of 5, of minus 5. So we take the next 2 bits, another 0, another shift. 1, 1, 1, 1, 0, 1, 1. Right? So what we computed is 0 times 5 times 2 to the power of 2 plus 0 times 5 times 2 to the power of 1 minus 1 times 5 times 2 to the power of 0. Right? Another representation of minus 5. A little bit boring, but now 7-bit. Then we take the next one. Now something happens, namely 0, 1. Huh? So we have an first add R. So we need to add, and now it's going to be a little bit difficult because I have to do this in my mind. We have to add 1, 0, 1, 0. Yeah, that is just for me as a helper here. So 1 plus 1 gives a 0, 1 carry. We have effectively here 1. 1 and 1 gives a 0, 1 carry. 1, 1 and 1 carry gives a 1 and 1 carry. 1 and 1 gives a 0. 1 carry, which is a carryover, which is due to the 2's complement. If we add a positive number to a negative number, we have a carryover sometimes, and it's just dropped. Okay? So, below we have 0, 1, 1. So, this should be plus 5, or 1 times plus 5 times 2 to the power of 3 plus 0. Yeah, I just put all of this here into the 0. Minus 1 times 5 times 2 to the power of 0. So 40, 39, right? So this here should be 39. What do we have here? This is 1, 2, 4, 8, 16, 32. Then we did somewhere a mistake, maybe here, because what should come out is the same, right? And is this correct, what I do? So the first shift is effectively after this one here. Then we process here 0, so we have another shift. We process 0, another shift. We process this one here. Huh? Yeah, there should be a shift, but a shift actually only causes, it doesn't change the value. Let me quickly think what I did probably wrong. Which one? This is 0, 1 is this shift, right? 1, 1, we have this shift. 1, 1, we have this shift. 0, 1 would be this shift. Just wonder why this is where I did, maybe I did a mistake somewhere. Give me a second. So minus 5 is correct, right? It's 0, 1, 1. Yeah, right? This should be correct because it's a shift. This should be correct as a shift. This should be correct as a shift. So I want to add 5, 0, 1, 0, 1. 1 plus 1 is a 0 and 1 carry. 1 carry plus 1 is a 0, 1 carry. 2 carries are 0, 1 carry. This drops out, and here we have a 1. So why am I wrong? Let me see. I do not see where the mistake is, sorry. The problem is that I was not able to compute correctly. So this here is 40. This here is minus 5, so it's 35, right? So we have this here minus 5 is 35. So we did here this decimal calculation wrong. This one here is 32 plus 2 plus 1 is 35. Yeah? Now it's correct. Yeah? Good. So, lucky enough. I did only something wrong in the decimal domain, not in the binary. Good. Next step. So we need the shift here. Next step, we add these two, which gives 1, 0, minus 1. So we need to add here the 1, 0, 1, 1. So 1 plus 0 gives a 1. 1 plus 1 gives a 0 and a carry. Carry plus 0 gives a 1. 1 plus 0 gives a 1. Right? The rest just remains. So what we have now is, for convenience, I just invert at 1. So we have minus, what is this? 0, 0, 1, 0, 1, 1, 0, 0. And then we have to add 1, so this here becomes a 1, right? So this is 1, 2, 4, 8, 16, 32. 32 plus 8, 40, plus 5, 45. Yeah? So, this here reflects the correct computation. So, this here is the correct result. So we wanted to compute minus 5 times minus 9. Interesting observation, we did not have to do any special things because this is a negative number. Yeah? You can try with a positive number, it also comes out correctly. Okay? Well, you could shift here, but it doesn't really matter. For the last step, you do not need. Because in the last step, effectively, this result is already correct. Yeah? If you shift, you waste effectively one register. You can do it, but it doesn't change your result. Yeah? It just extends the result by 1 bit. Yeah? So I probably take a picture of this and load it up later. Let me see if I can get this somehow. Good. So far, okay? Yes. Can you be a little? I don't hear. Sorry. So what is it? This here? Well, this is just a helper for me. So this additional line here is just a helper for me because I needed to add to this the R. Yeah. So sorry. We need effectively for this here. I've forgotten to write this there. This here gives effectively minus R, right? And this minus R, just for me as a helper, I put here because I need to build the sum now between that one here and that one here. Yeah, because this here is just minus R. Yeah? So you could remove this, but I need this to compute it in my head to make no mistakes here. Okay? So this here is unrelated to the algorithm, this here is unrelated to the algorithm, that's just this here, this value, and I need this as a helper. Yeah? Okay, can we go ahead? Then, yes, that we did. Now, as always, we can make it a little bit more tricky. Can I remove this? Yeah. As always, we can make it a little bit more tricky. So what we have here is actually what we did all the time now. Yeah? We have this here, a 2's complement number. Yeah? To this 2's complement number, we add an artificial 0. Yeah? This is just a mathematical description of a 2's complement number. This is actually just a representation, this number. Huh? And then what I do, I form pairs of mi and mni. So to be able to do this, I take, I multiply mi by 2, subtract mi. So I always make an operation like 2 to the power of I plus 1 mi minus 2 to the power of I mi. Yeah? So effectively I have each term here twice, once with 2 to the power of I, once with 2 to the power I plus 1. Then I can build tuples out of that, and I can always collect the same powers of 2, giving that I have 2 to the power of I, mi minus 1, minus mi. Yeah? That's just if I add here now, let's say, plus 2 to the power of I, mi minus 1, minus 2 to the power of I